to try to understanding, but really there is no magic measuring tape that we can extend out to a star to measure its distance. It's the scientific method. That's how I would answer it, and it's how I explain it to middle school children.
I would just add to that that you can never prove a theory right. You can only prove it wrong.
Sorry, I'm trying to recover. Zoom closed. That's why it stopped working.
As Danny said, scientific method, which is, repeat experiments, see if, different ways, different people measuring with their thumbs get the same answer, right? And that should get us a good handle on it, unless there are systematics, right? Everybody has different things. So, we can only do as much as the scientific method allows us.
So is our science a predictive one? Is astrophysics a predictive science? Do we try to make predictions that we check with observations?
Well, you should talk to the simulators there, but generally, the simulators will come up with this. Likewise, Kanin showed some of the laboratory work, and I know that's one of the other questions, but the laboratory work can make suggestions for things we might find. I mean, to use a fun example is the buckyballs, right? Predictive of emission features that people try to look for in the ISM. And so, definitely there are predictive things we can do out there. And that's also part of the proposals too, is trying to say we expect to see this based on this simulation, this laboratory work, or this observation in another galaxy. So it is predictive in terms of that respect.
Sometimes it's the other way around. We get observations that the models can't explain, and then the modelers or simulators have to go back to the drawing board to explain it. Like, for example, SO2 in a recent planet atmosphere, I think.
No, but I think it's a very good point. I think our science should be a predictive science. And for all the simulators in the room, don't hesitate to, it's a bit scary, right? Like, you have simulations. Do you dare to make predictions of what we should observe either next year or even in 10 or 20 years, right? You might not get the answer right now. It might be scary because it might be proven wrong, but that's the only way we go forward. It's people making predictions and observers trying to disprove them, as Julia said. And that's not bad, even if your prediction was proven wrong. I think that's how we make progress in science. And for observers, we should also really try to make sense of the observations, not just collect things in a way, but also try to compare with simulations to try to disprove predictions or maybe find new things. And I think it's actually not too bad. Like, you can always have more synergy between observations and simulations, but I think we're getting there, especially in the ISM science, I find.
Any of simulator or observers who wants to comment on this one?
We are way behind as theorists. So will you please stop observing and making new instruments? We have so many things to explain that we don't know, and new instruments are bringing us new surprises. So I feel it's very hard to make predictions as theorists.
Any other
What do you
comments?
think?
Other simulator or modelers? In fact, they left. The professor left because he didn't want it to be asked this question. No, one thing I think is important in knowing that we cannot go there is consistency. I think one main key in this business is trying to get the same answer with different answers, for instance, to get consistent answer with different answers. And this is a tough job in general. So
maybe kind of going off that, I think something that I've seen as I bounce around is that you can look at a big sample of galaxies and kind of see general properties, but then if you look at one individual galaxy and compare that to any other, you find that every individual galaxy is very different. So how do you, I guess this is like kind of the next step of the Milky Way to other galaxies. How do you connect other galaxies when every galaxy seems to be its own special snowflake?
Well, we hope that we observe that they, even if they're individual snowflakes, their population has some collective behavior that we can attempt to understand. And I think that's that actually is part of what makes nearby galaxies so fun, that, they do have collective properties that are predictable potentially, and you can measure and quantify, but that each individual one then is going to be doing its own weird thing, just like our special kiloparsec of the Milky Way, with our little local bubble and expanding shell and all of that. So it's interesting, right? Because there's like complexity on many different like levels of the problem, but then predictability on a higher level, which is I think really interesting. That's what the ISM is doing, right? It's like a complex system that we're trying to piece by piece understand, but also understand the whole complexity of the system working together. And I don't know about the rest of you, but that's why this is fun. That kind of problem. We're all here to solve that kind of weird problem, which, yeah.
Yeah, do they follow a standard scaling relation, right? Like the star forming main sequence. And then some of us just can't resist to look at the outliers and maybe study the green valley or the red cloud. So that's how we would think of it, Jessica, right? They follow a scaling relation, and then are we going to follow up on the outliers, and why are they outliers? That's a lot of astronomy right there.
The other thing to remember is that the underlying physics is the same, right? People have been trying to see if physics breaks down as we go back in time, as at different environments, and so far, everything seems to follow the same physical laws. So, having a look at the differences, like Danny says, can give us clues for why some things are the same, why these outliers. So the underlying physics, the underlying causes are always going to be the same. It's just then that variety tells, well, if you tweak this condition, you end up with a slightly different looking object.
one thing I think is important on this topic is the fact that because ESM is a complex system, there are emerging phenomena. It's not, the nature is maybe it's exploring all the parameter space, but it's locked into subspace and of the parameter space. And those are kind of laws we are trying to find. So the laws of, what are the laws of star formations? What are the laws of galaxy formations? And stuff like that. And this is because of the complexity that there are some nonlinear physics that you have emerging phenomenon due to this. Questions, other questions, comment on this subject? So we're not speaking so much about imperfect data reductions because we are doing mostly science, but this happens even if we're trying not. So what is the impact of imperfect data reductions on the fact that we are only remote sensing, and how do we fight this in your experience? Do we?
Data reduction? Well, so, I feel like imperfect data reduction, if we frame it that way, it's like, here's a big problem we have to fix, right? And I would say that, data reduction itself is not always a solved problem. right? Like we may not actually know when it's imperfect always, but this is another thing that we're continuing to improve. So I think, you know, the kind of maybe more optimistic way to frame it
Yeah,
is
I agree.
how,
Let's be optimistic.
yeah,
But
that,
my point is not to be pessimistic, but to ask questions that we have to ask in our science.
right. But I feel like you can, you know, there's going to be data reduction involved if you're an observer, right? You're going to get there's going to be a lot of choices that may not be easy choices. You know, some types of data reduction are particularly complicated. For instance, like maybe you're doing some interferometry observations. Those are always challenging. And there's, you know, things built into the reduction that, you know, you might not have that much control over that are big assumptions and so on. So this is a thing that will be occurring, but, you know, I think the path forward, right, is that we have tried different things. We have different tracers, we have different experiments, that data reduction becomes part of the overall like challenge, part of the overall part of or kind of setup, that this is included in how you assess your uncertainties, how you assess your biases, that kind of thing. So I feel like I wouldn't frame it as like what happens when there's bad data reduction. I mean, there will always at some level be bad data reduction. There's no way around that. That's part of the approach, right? I don't know if anyone else wants to add.
A little bit of a different way to look at this, both from my experience with Spitzer spectroscopy and Herschel spectroscopy. When we first got those complicated data sets, it was super disappointing, and we thought we had no detections, and we wasted so much time on those telescopes. And this is where perseverance, I feel like, is a very useful trait for anybody, you know, especially a scientist. Talk to a lot of people, maybe at the telescope headquarters, other teams, and stick with it, because we ended up getting fantastic data. It's not quite what you were asking, Jerome, but perseverance there, because it was really scary actually at the beginning, and then in the end it turned out great.
Yeah, I can relate to that experience also with Herschel imaging on very wide fields. So perseverance is key. I think there's always a way to improve on data reduction. I don't think it's as open-ended as, say, you know, like a science question for which maybe you don't quite have the tracers or the spectral or spatial resolution. I would also say that, I don't know, I work on space telescopes, and we make a big effort to deliver science-ready data. And I think that's a huge help in terms of like minimizing the overhead for research teams that they spend on, you know, trying to fix little things here and there or major things here and there. And so you know, my hope is in the future, maybe some of the major ground-based observatory follow the same strategy and try to kind of centralize as much of the data reduction as possible.
That's for sure. I think we are going into the directions, but it also means that the community needs to fund people to do these efforts. And this is not free.
So I just want to, this may not be directly related to the questions at hand, but I was just talking to the students yesterday. I feel like there's a growing divergence between those who do science and those who build instruments and therefore understand the data best. And there's also difference between wavelengths. For example, I mean, being an optical observer, I still talk to people who literally build their own instrument, I mean, their own telescope, buy their own camera, and then take data and reduce data all, you know, in one go. That's still manageable. But talking to space telescopes, talking to radio, some millimeter observers, it seems like there's a gap, especially between students and the observatory. I think so the data are delivered to your office. And that makes me a little worried. But maybe it's not a big problem, but I just think there may be some effort needed to there's a growing need of trying to build this synergy to bridge that gap. I'm a little worried about how people don't have a real sense of how data were taken, what's required to calibrate the data, what will be the potential issue. So for those who want to be aiming to do empirical science, I think it's really important to understand your tool, but I'm not sure how to make that happen.
Any comment on this one?
Two comment, one for the first part, which is, of course, apart from everything else, people have said that people do a lot of effort into this. One of the ways we do this is repeat observations, whether it be, interferometric versus single dish, whether it be, repeating with the same object like Sloan has done with spectra to calibrate the uncertainties, whether it be comparing your data with somebody else's data, which is at lower resolution. This is the best way we can try and get the systematics of data reduction. But go to the Solen's point that at some point we're going to have that separation. So go to SKA. We are not going to be dealing with the raw data there because it's just too much. And so the people at the SKA observatory are going to do all the reduction via the supercomputers and get us data in a manageable form. And so the only way we're going to get a handle on what the systematics are, we need to talk to the people. And so have that communication pathway going. And I know the SKA Observatory are trying to do that actively, keep at that, but we're never going to get our hands on that raw data because it's just too much.
Well, the positive side of your question is, I think this is just the way toward professionalization in the instrumental, and I think this is related to the question of data reductions. In fact, because there is professionalizations, probably the difficulty in doing data reductions, the uncertainty in data reductions is reduced. It's a bit like computers. Computers are extremely complicated beasts, but all of us are relying on them. And sometimes it's the other way of the other side of the medal is that when there are problems in observatories, they need to be advertised. And this, everybody has to realize that this can happen, okay?
And maybe on that same point, I totally agree with you. I think it's, I don't know if it's unavoidable, but as Jérôme said, yeah, things are getting more complex. If you want to do multi-wavelengths interpretation, because we just said at the beginning, we need multi-wavelengths. Okay, but you can't be an expert in the data reduction of all of these wavelengths. I think this is getting so difficult. And in a way, it's exactly the same thing that happens if you want to compare observations and simulations. When you're on one side, you typically don't understand all the details of the other side. And that's why we really need to, interact with each other and keep really a strong synergy. You will never be an expert of everything. But yeah, it's important to try and understand what are the limitations of the data, of the simulation, before doing any kind of interpretation that, will probably be over-interpretation without that.
Maybe I can add related to that, maybe as an experimentalist, I would say that it's important that young students and young researchers can actually go to ground-based telescopes and make some observation by their own. They won't be able to do that in all the wavelengths range, but at least having done it once, you kind of better realize what is behind getting your observation. It's not a complete answer, but I think it helps.
Who did already went to a telescopes and did observations by themselves? No, that's not what she said. She said, we're not speaking about the data you're working on. We are speaking about going to small telescopes on grounds to see what are the problems. Okay, during your studies in France, there are several masters that are going to taking the students to small telescopes to try to teach them to give a sense of the difficulties in doing observation to the student.
I think that that's a very valuable thing to learn. It is also possible, though, to, you know, have a very important and thorough and, you know, well-researched PhD or project that involves data from telescopes that you could never, you know, so there's going to be a lot more of that in our future too, because archival data from, you know, Rubin Observatory, from a bunch of space telescopes, from you can design experiments that are more into data science, maybe, that don't necessarily involve, you know, reducing data from any particular telescope. And so this is I would say it's a very useful experience, and it's like something to learn and something to, you know, have for your future. But we should also, I think, not insist that that is part of some of a necessarily a PhD in this topic.
Yeah, I was going to compliment that because, you know, of course, yes, there's telescopes that you can never go to, or actually the way we observe with them now is not, it's all remote. But I think it's important to not be shy and ask a lot of questions, and also make sure that on your analysis team or proposing team or whatever, you have maybe one expert on the observatory who can maybe point out some of the subtle challenges, or, oh, wait, did you think about that? Maybe that limitation in the data reduction or the way the data are taken will affect the way you can measure whatever parameters you're after. And so, you know, sending them an email if they're not on your team, or, you know, just asking a lot of questions just to make sure you have the big picture on what the challenges and limitations are with the data.
Another things we can say is that most often we hear a lot about stars in the field. Stars, I mean human in the field that make that you see, for instance, EHT. You see that you have the guy who say, "I did it. Okay, I made all those telescopes to work together to observe the first black holes." But in fact, reality is not this. Reality is that most of the money, most of the position in our fields are in observatories. Okay, so a large fraction of the people who actually ensure that this is possible is not the guy who is publishing. It's all the collective efforts. Well, at least that's my view.
Maybe just a quick note. When I think maybe we can agree that the detection of gravitational waves is one of the biggest shining moment and success in the general astrophysics research. And when the first detection came out, the U.S. National Science Foundation held a press conference, and Ray Wise, being one of the PIs that had that was behind the scene making it happen for 4 decades. The first thing he said was, the LIGO experiment is a great demonstration, successful demonstration of a fruitful collaboration between engineers and physicists. He attributed the success to, the engineers coming up with the necessary technique to isolate all the vibrations in the environment. So I think it's important. I'm not saying you are doing this now, but always keep an open mind. Make sure you talk to people outside of your particular expertise area, and try to learn from try to find people who can complement your own expertise, and maybe in the short-term or long-term future, you can come together and really make something original and exciting happen. Just, keep that in mind.
Yeah, I can only second that. I mean, the one thing, if nothing else, take away from this ISM school is to use the strengths of others, right? I mean, each person has their own expertise. I asked Jackie, like questions about, metals, how they form, what do we expect to see? Karen, I always go to in terms of the dust, the pHs, things like this. Jerome helps me immensely in terms of the molecular gas. Right. So each person has really helped me get a better picture for this. And it's from this that we get these great collaborations and we move forward. So, build collaborations, talk to people, learn their expertise, help each other, and you end up with better science.
Is there someone who wants to? No, wait for the microphone, please.
So you talk about leaning on collaborations and, it's great being at a grad student and a huge institute that has a ton of researchers, but you also hear of more and more positions being in sort of isolated, there's like 2 astronomers in the department, and like, how do you maintain collaborations and like keep yourself like engaged with the broader scientific community, other than just Zoom call. And B, do you have any advice regarding like the future of the job industry for us all? Because there's 70 students here and 15, tenured organizers. Any advice or words of wisdom in that regard?
Ooh, let me go for the first one first, because that's easier. Speaking as Australian, collaborating around the world, Zoom calls, Slack, Overleaf. Our job is, in terms of interactions and networks, is actually easier these days than back it was, like in the early days, where it was just email. So, it's thanks to Zoom that I'm able to keep these collaborations, Overleaf that I'm able to work on, like multiple papers, Slack channels to sort of keep up to date with some of these things. Sometimes it's a bit too much, but, it's thanks to these I'm able to do this. And, and then the occasional travel where I'm now able to chat person to person, sort of work on things like this. So yes, personal contact helps. So definitely try and talk to people face to face when you get a chance. Work with this. This goes whether at a big institute, a small institute, right? You're going to have colleagues, friends, whatever, at different institutes. And so use whatever network tools you have. For the second question.
Maybe let's stay on the first one first.
No, yeah, just to add to that, I can only relate that if you go to a conference, go talk to as many people as you can. And, not everything will lead to collaboration, but that doesn't matter. If you have talked to somebody face to face once, then later on, if you see a paper from them, it's going to be easy to just send them an email, ask questions, right? You shouldn't be afraid of doing that. People are super happy to actually get an email when they've published a paper, just, to get a question, something you haven't understood. So yeah, don't be shy.
I just want to add, you are here, you did the right thing. And really many thanks to the organizer to put this summer school together. This is a chance for everybody from different backgrounds to come together. So to make sure another opportunity comes along, jump on it, make every effort to attend, but to a limit, right? There's so much time you can spend at the conference. The rest, you still need to do research. So on the second question, I just want to add that I know we all have a dream we want to pursue, but I think there's some benefit to make that dream as wide and broad as possible. Cultivate multi-interest. But so I don't want to give false hope, but things do happen. At the University of Chicago, we are having a new faculty joining us. And this person really took a break to go working in the industry for a couple of years. And then he returned to ask for research. So I think it's really important to keep an open mind and just make sure you're enjoying what you do. Because if you're interested in what you do, I think there's a better chance to be successful and productive. And if you are productive, and it may be more, I don't know, healthy, maybe that sounds a little condescending, but it's just better all around to think that you are hot commodity on the market, that it's up to them. I mean, it's up to you to decide where you want to go. Keep that mindset. I know it's hard at this stage. I went through that. I still remember that. But really just trust there are multiple choices in life. And then things will come along. Just have to trust that.
Yeah, just back to question one, I guess for a bit. Also remember that a lot of institutions, especially large institutions, have visiting programs. And so if you're part of a large collaboration, and hopefully you are, you can go visit a collaborator for a month and they will help fund the trip. And so that's one way where you can, at least temporarily be in a maybe more lively, larger institution to do your research and closer to the people that you work with. Second question, I think perseverance will also come into play, right? There's a lot of rejection before you get successful. And so, building that thick skin and persevering, keeping your enthusiasm and your energy will be important. There's a lot of opportunities out there. If you're free to move around geographically, I know sometimes that's not possible. But I think trying to keep an open mind as well will help.
I agree with Melanie. Try to have lunch or dinner with different people every single day at a conference. Don't be shy. Go up to their poster after their talk. Get that network developed. I love the idea of externships. Go to STSCI, for example, as a pre-doc extern. Really good way to network. And don't be afraid of going to a job fair and just seeing what's there.
Yeah, I'm not sure. So on the first part about collaborations, I don't think there's any better way than Zoom or Slack or whatever. There's no obvious solution to this. But
I agree with that. Even in an institute where you have tens of astronomers, in fact, you're spending quite a large fraction of your day in Zoom today.
But I think you can learn to use Zoom maybe in a way that's more fruitful, right? Like, and this is probably going to be annoying for me to say, but like have your video on and like engage with people, right? And like, look, you get some face-to-face contact, you're like interacting with them, you have to participate. It's easy to be kind of video off, like not doing anything, and that won't be helpful. For me, I like feel very alone if people don't have their video on and I'm like, just sitting there trying to get people to talk to each other or something, like, anyway, this is getting kind of random, but this is what we've got. And it's actually a pretty good solution if you think about it. It's not bad. Could have been a lot worse. So, yeah. And I don't, oh, go ahead.
I'm sorry. Go ahead, please.
I don't have anything particularly insightful about the job part. It's a challenging problem, but I think the main thing is to understand what kind of problems you like to solve. And I don't think those, like for most of us here who are doing, research into a complicated system that we like to take apart, that's not going to necessarily have to be specific to a question in astrophysics. And you can think about whether that type of problem solving and whether that type of thing has to be specifically the ISM, or would you be interested in that as well in many other fields? So I think that, there's a lot of opportunities for very cool jobs in astronomy that, you might want to broaden horizons to like different kinds of positions, not just, research faculty or something like that. There are lots of research faculty jobs too, though, in some countries. So keep that in mind. And, I think the basic thing though is to try to understand what satisfies you, like what kind of problem solving and research satisfies you. And does that have to specifically be in a certain field and a certain type of position? Or can you find fulfillment doing that in many different ways? Sorry, that feels very negative in a way, but I think.
No, I don't think so. I think that's fair. And there are plenty of opportunities. Try to find the ones for which you will have fun. Okay, try to make your life fun. That's all. And then there are many things we don't control in life.
Yeah, since we're talking about a lot of data is coming from all the telescopes, and there are a lot of archival data already with us. And we are like modeling nowadays, all of us almost writing codes for our simulations. So, and we were talking to each of us, we are mostly like simulators, modeling, and observers. So I think at this point of time, when we're talking to engineers for understanding the instrument, I think it will be also good that we'll get to talk to people who develop all these softwares and the pipelines who are running them, because sometimes it's really hard to understand the pipelines.
And in fact, I think you're completely right. And in fact, I think it will be even more interesting in the future because of machine learning, statistical stuff. Okay, I think we still have 10, 15 minutes maybe. Let's speak about current and future trends. So, okay.
Sorry, maybe before we talk about the machine learning, I ask some general questions about like learning and doing research. Because I talk with different people, I feel, okay, everyone is doing very amazing, interesting topic, but I feel there are like facts, there are like individual points. It's difficult for me to link different people's research together. It's like, I cannot find the link between different projects. I find that's a difficulty for me. And another thing is because we are doing very highly specialized project. So it's like we're doing the research that no one has done before. Of course, we have our supervisors, our collaborators, we get best support. But sometimes I still find the difficulty to justify or make the persuasive enough to say, okay, what I'm doing is the right thing, and I'm approaching the truth. I just wonder about how do you just go through this like an uncertain stage, like a, I don't know, make it persuasive for other people and also for yourself.
I have an answer to this is you're not alone. Okay, I think we all went on this. Astrophysics is a strange beast. Interstellar matter medium is even a stranger beast. Okay, so we all arrived in PhD without a good idea of where to go and so on. And the way to go forward is to go to schools and to go to conferences, because on those spots you see many different. You have a broad view of the stuff. And you can see, I'm trying to, maybe I'm doing too much advertisements to funds, but you know, funds has been a huge collaborations, and there are ways to join it. Okay, so you need to be curious about what's going on.
Yeah, exactly. I think curious is the right word. Be open-minded, talk to people. And that goes both ways, right? If you try to explain your topic to somebody that is doing something completely different, I think that's a very good way to try and take a step back. It might be difficult, especially at the beginning of your PhD. You go deep down, and that's necessary. You have to understand the details of things. But especially as you go towards the end of your PhD, really try and take a step back. So it's talking to people, trying to explain why what you're doing matters, not just for you, but for science in general. Read the literature. What are the big questions in the field, and how do you contribute to answer them? Yeah, I think these are the advice I would give you to see how your work is relevant to other people, and at the same time, see how other people's work can be relevant to what you're doing.
Just add one more point to that. I agree with Jerome that, we all go through this, especially in our PhD. We dive deep down and it gets narrower and narrower. And so we can't see the relevance to everything else. So what Melanie said is great in terms of what you do. The other point is talk about your stuff and you'll find people come to you as well, right? They'll say, oh, that's interesting. I want to do this, this, and this. And you'll find connections, right? So listening to all of your lightning talks, I wanted to talk to all of you, right? Because I found it all interesting. And so, this is the way to do it, is that, realize that while your topic is narrow, it's relevant to a lot of what we're talking about here.
Yes, so more or less as a reply from a fellow PhD student who was overwhelmed with all the interesting research of everyone that has been doing when I visited my first school, and it was more or less just starting my PhD. I remember making lists of every single topic that the people that I talked to were interested in and working on, and just trying to see how I can make bridges in how would it connect to my own research topic. And from that, I made a lot of friends that are in completely different fields, where I'm an observer and are people in a simulation group that I'm now working with, or people that are in the modeling aspect of clouds using the multi-GISM model that some of you are now working on in the Ensemble project. And in that way, I more or less learn more from other people about what I'm doing than what I'm doing in my own research. And it motivates me to actually learn more about what I'm doing than helping others as well. It makes it very interesting. So that's why I'm grateful to actually be in a school like this again and talk with all these people here and with the professors as well that are expertise in a field where I eventually want to become an expert in, hopefully as soon as possible, or at least I want to work as hard as I can to get in there. But the scary step of starting from nowhere or thinking, there are so many people far ahead of you and you just started, how am I going to get there? It's just a step-by-step process of talking with a lot of people, reading literature of the people that are in your university or research team that more often than not are also in different fields, and then talking with those as well, practicing that in schools and also then learning people so that you have collaborations abroad. And then you start realizing that you're sitting next to someone that does almost the same thing as you. It's like a step-by-step process. And at some point you actually get to a point where you want to be, where you thought, oh, I'm too scared to actually go through that process to get there.
Also, very quickly, I think these are good advice. Very quickly, one advice I've been given when I was a PhD student is every time you listen to a talk, a seminar, or whatever at a conference, make yourself think of a question that you would ask, even if you don't end up asking it. But often that will be a question that is related, that is trying to connect your work to that topic, even if it's completely different.
And one last point on this, I think it's okay to sometimes go to conferences in slightly adjacent fields, right? Like I mostly go to ISM conferences, but I've been to conferences on the high redshift universe, chemical evolutions, the baryon cycle and stuff like that. And I ended up talking to people, it's like, oh, wait a minute, you need this constraint from the local universe. Well, I can work on that. I can help. And this is how I ended up working on Damp-Lyman alpha systems at high redshift, which, that is not at all related to my PhD topic. So, I know there's limited opportunities to travel, but I think maybe every now and then, go to a conference that is not your field, not completely different, maybe not exoplanet atmospheres or whatever, but like slightly adjacent so there can be some cross-fertilization and you can really get the big picture of why your research is important in the context of general astrophysics.
Okay, so we have to wrap up. So
just one quick last point. You are looking at the life example. I've been a professor at the University of Chicago for many years. I came here. When I came, I didn't know anybody in this room. I think it's a fair statement. So learning is a continuing process, never stopped. So it's better to start early.
So, last questions. What are you excited on, and what will you be excited on in the next 10 years? Just to be optimistic at the end.
Yeah, I can't say next 10 years.
We'll
because,
take the times. We won't get coffee.
Yeah, we're all excited about GWST. I think most of us, right? So, it really is a groundbreaking thing. Seeing the bubbles in nearby galaxies. We've seen 6 to 8 so many times, but I still am captivated.
Also, not to repeat James Webb, but to go back to your question that we didn't address, machine learning. I think that's the big thing that is starting now that will be super important in 10 years. We're getting so many data and things are getting so difficult to interpret that I think this is really the next big thing.
Very similar. So I think this is a golden era to do astrophysics research, particularly in observation. With all the new tools, new instruments, new telescopes coming online, I feel really sympathetic for the theorists. They have a hard time to catch up. It's really true. So really we are very lucky. So that's what I'm most excited about, all the data that are coming our way.
Two things. Number one, I'm excited about basically juicing out all the possible science that we can do with UV spectroscopy with Hubble until it goes away. I think we have a good 10 years probably. And number two, exploring pHs at very low metallicity, which we started to do with Webb.
I keep a file, I call it tomorrow.txt, just ideas that I come up with. I would like to know the far infrared emission properties of AGN and how to disentangle it from the disks that surround AGN and just the capabilities we have right now. It's not possible to do that. I'm looking for the future there.
I am very excited to figure out how pause form. I think we should really do that. That would be very interesting to know. And I think we will with JWST. So, and other things. I mean, people are doing amazing work looking for signatures of gas phase chemistry and molecular clouds in the Milky Way and so on. So I am really looking forward to that. And many other things we're going to learn about the ISM.
Thinking of the future, I mean, we've got Roman coming up soon. We've got 2 big ELTs coming up. We can see the construction happening, right? There's going to be some huge, amazing data coming out. Machine learning is getting faster and faster at getting archive data. So we really are an exciting era building all of this together.
Karin, what are you excited on?
Yeah, I would say GWST also. I did my PhD on ISO, so GWST is great. And well, from the lab point of view, maybe investigate pH formation, which is a really tough subject.
Any people wants to comment on this one? Okay, so I propose that we close. I would like to finish with the idea that one of the central topics about this school is interstellar medium. And I think you make the right choice in studying this because you have plenty of physics into the interstellar mediums. Physics, complexity, and we know that in our worlds, complexity and is one of the key of the understanding of the future. So I really think that there is a bright future in interstellar medium studies. Let's have coffee.